Welcome to this explainer. Okay, let's jump right in. Today, we're stepping into the high-stakes world of a doctoral research lab, playing out almost like a suspenseful academic comic book. Our mission? To totally master the justification of partial least squares structural equation modeling, or PLS-SEM. You know, whether you're a PhD scholar, an MBA student, or an early career researcher, defending your methodology is basically a rite of passage. So let's step into the panels of our story and set the scene. Picture this, a quiet, incredibly tense viva room. Our protagonist, a very sweaty, very nervous PhD student, is trapped in the hot seat. Across the table sits the formidable viva examiner, peering over their glasses, and they launch this absolute missile of a question. Why did you use PLS-SEM instead of CB-SEM? It's the kind of question that literally freezes our student right in their tracks. But before the panic can completely take over, let's initiate a flashback. We go back to a previous lab meeting where the student's brilliant research mentor steps in with some crucial advice. The mentor explains that you can't just give a one-word answer here. A true rock-solid defense is a web of logic. Your answer must connect the method itself, the state of your theory, the complexity of your model, the exact condition of your data, and your ultimate research purpose. Let's break down exactly what this mentor taught our student. Starting with Section 1, CB-SEM versus PLS-SEM. To actually defend the method, we first need to get a grip on how these two tools fundamentally differ. The mentor starts by defining PLS-SEM as a variance-based approach. The entire engine of this method is driven by prediction. It uses ordinary least squares regression with one primary statistical objective in mind, minimizing the unexplained variance in your dependent variables. Or, to look at it from the bright side, it aims to maximize the explained variance, that crucial R-squared value, in your target constructs. On the flip side, we have CB-SEM. This is a covariance-based method with a totally different objective. It is built from the ground up for theory confirmation. It essentially asks, does our theoretical model perfectly match reality? It tries to estimate a new covariance matrix that isn't significantly different from the original observed covariance matrix. Ultimately, it wants a goodness of fit. And that right there highlights the core philosophical split between the two methods. Think of it like this. CB-SEM is looking backward, validating what we already believe to be true with well-established theory. PLS-SEM, however, is looking forward. It's asking how well our model can actually predict the key outcomes we care about. Neither is universally better, right? They just have entirely different jobs to do. Which brings us to Section 2, when to choose PLS-SEM. Now that we grasp that fundamental difference, when is it actually the right, methodologically sound choice? Well, the academic literature provides some pretty clear guidelines pointing straight towards statistical power and prediction. PLS-SEM naturally has higher statistical power than CB-SEM, which makes it absolutely perfect for exploratory predictive research. You know, those situations where the theory is a bit less developed and you're trying to map out brand new relationships rather than just confirming decades-old frameworks. So the takeaway here is that you choose PLS-SEM based on a very specific checklist. You choose it when your study focuses heavily on prediction and explaining variance. You choose it when your theory is still actively developing. You also want it for complex structural models. We're talking lots of constructs, indicators, or paths, because PLS-SEM isn't choked by the same mathematical identification constraints as CB-SEM. Plus, because it's a non-parametric method, it is incredibly robust when your data simply do not follow a normal distribution. It handles the messy reality of data beautifully. Let's ground this with Section 3, a predictive model example. To really see how this builds our students' defense, let's look at a concrete research scenario. Imagine an early career research project mapped out on a lab whiteboard. The topic? Digital transformation and workforce competence in construction projects. We have 4 independent constructs: technology integration, training support, worker well-being, and team communication. And they are all pointing toward our target, the dependent construct, workforce competence. The mentor uses this exact setup to anchor the methodology directly to the practical goals of the research. In a rapidly developing field like digital transformation in construction, we simply don't have 50 years of rigid, established theory to fall back on. We want to know, do these 4 factors actually predict whether a workforce is competent? And exactly how much of that competence can we accurately explain? That is a purely predictive goal, and it is absolutely screaming for PLS-SEM. Moving right along to Section 4, composite scores and assessment. Okay, before our student can face the viva, they have to understand how this method mechanically handles data. PLS-SEM is super unique in how it creates variables. In CBSEM, estimating latent variables suffers from factor indeterminacy. Basically, there are infinite possible scores, making prediction really messy. But PLS-SEM actually estimates specific, determinate composite scores for every single observation. These scores act as exact proxies for your abstract, latent concepts, allowing the algorithm to run precise regressions and examine the relationships among the constructs. Because this mathematical engine under the hood is so different, we don't evaluate it using traditional goodness of fit metrics like chi-square. Instead, we follow a specific two-step process. First, we evaluate the measurement models, checking reliability and validity. Then, we evaluate the structural model, which is entirely focused on maximizing that explained variance and proving out the model's predictive capabilities. To actually prove the model's worth to that tough examiner, you have to systematically assess a few very specific metrics. You look at R-squared, the amount of variance you've explained. You check the path coefficients to see which variables are doing the heavy lifting. You analyze the effect sizes to see how much a specific predictor actually contributes. And you look at predictive relevance to make sure your model can actually predict data it hasn't even seen yet. Now pay close attention to Section 5, Common Mistakes. To guarantee a flawless defense, our student also needs to know exactly what terrible justifications to avoid. Please avoid these amateur pitfalls. Do not say you used PLS-SEM only because your sample size was small. Yes, it handles small samples well, but that's not its main purpose. Do not use it just because your CBSEM results were weak and you panicked for a backup plan. Do not claim it's somehow mathematically better, it's just different. Don't ignore theory entirely. Don't obsess solely over p-values. And finally, never report an R-squared value without context. An R-squared of 0.25 might be laughed at in physics, but it could be a massive breakthrough in consumer behavior. And we are back in the room. Section 6, the viva defense. Armed with this deep, structured knowledge about variance, composite scores, and exactly what pitfalls to avoid, our flashback ends. We snap right back to reality in that hot seat. The examiner is waiting expectantly, our student takes a deep breath, looks the examiner right in the eye, and delivers this perfectly structured, comprehensive answer. They don't just throw out academic buzzwords. They directly link the inherent statistical nature of PLS-SEM, handling complexity and focusing on prediction, straight to the unique reality of their construction workforce research. It's a beautiful moment. And then, the tension finally breaks. The formidable examiner lowers their glasses, smiles just a little bit, and concedes. They acknowledge the rigorous, scientifically valid defense. Our student hasn't just clicked buttons in a software tool. They've proven they understand the very statistical foundation of why that tool exists in the first place. We're going to leave you with this final, crucial thought that summarizes exactly when to leverage this incredibly powerful statistical tool. PLS-SEM is strongest when the study aims to predict, explain variance, and develop theory through a complex model. So the next time you sit down to map out the intricate, messy realities of your own field, will your model be robust enough to predict the future, or are you just confirming the past?